Okay, so I already put some things on the blackboard, but this is just a review what we did last lesson. Last lesson we constructed the path integral for this kind of Hamiltonian. So this is the prototype of Hamiltonian that we look at in quantum mechanics. Here for a one-dimensional problem where P is the one-dimensional momentum, Q is the one-dimensional position operator. But I mean the generalization is just straightforward. Okay, so just to save some space, I write one dimension, but just go through for unclear dimensions. So what we did is we arrived at some path integral representation of this transition amplitude. So I tried to motivate that this kind of object is very interesting, especially when it comes to more complicated problems where we cannot really do any more what we do like in the first courses of quantum mechanics, like solving the Schrödinger equation. It's like the propagator of the theory, which contains all the relevant information, in the sense that this is always related to observables that we want to calculate. And another thing is that this is really generalized to the many-body context. And what we actually did is we derived the right-hand side. So we started out from this matrix element, and then recognized that the problem here in writing down immediately such a matrix element lies in the fact that the Hamiltonian consists of two parts. One operator which depends on P, another part is an operator which depends on Q, and they do not commute. So if one has just one of these components, it's very easy. One can write down such a transition amplitude just by going to the corresponding eigenbasis. So here we have two operators which cannot be diagonalized simultaneously. And what we did is, in a way, we exchanged the fact that we have here non-commuting operators. We exchanged these non-commuting operators by some numbers, by the eigenvalues, but how to do this trick was we had to go from a theory which talks about the point-like particles, like the position of the particle, to some one-dimensional object. Okay? This is always the scheme how the path integral or function integral method works. We try to substitute operators by C numbers, but we can only do this in some clever limit by dividing the time evolution in many small steps, then looking at the approximated evolution for a short time step, where we can then, in a way, write the evolution operator in a form that can immediately calculate the matrix element of the short time evolution, and then we have to sum up all the time steps, and by this we arrive at an object which is one dimension higher. So the quantum mechanics become from the dynamics of a point particle to integrals here over path in classical phase space. So what we find is that the transition amplitude, let's say you have a particle at position qi, and you ask what is the amplitude that after a time t, this particle can be found at position qf. We find that this transition amplitude is given by an integral over all possible paths connecting these two coordinates within a time t. So we have to sum over all paths, and what we do is we have to give every path a weight, which is just the classical action of the corresponding path. Okay, and this, how we derived it, was inserting, always the eigenstates for the P and Q operator. So naturally we arrived here at path integral formulation, which is also called the Hamiltonian formulation of the path integral, because here we really talk about path in classical phase space, and this is the Hamiltonian version of the action. Okay? So of course, the path integral has to satisfy these boundary conditions. Now, what I just mentioned at the end of the lecture is that, well, you can, if you recall the properties of Gaussian integrals, you will see that this is just a simple Gaussian integral in P, in momentum. You can integrate here over all momenta and arrive at the representation of this transition amplitude, which is now not over path in phase space, but just an integral over path in coordinate space, again with the corresponding boundary conditions. And again, we find that each path is weighted with the classical action, but now in the Gaussian formulation. So this is Now, the path integral over path in coordinate space, you can work with either of the two versions. It's just a Lagrangian version. Now, there's one thing that we said, so in a way, all the derivation is quite straightforward. At one point, however, there's some limit n to infinity involved. And this is, I mean, mathematically not that well defined, but I mean, we are physicists, we are practical. If we are not feeling too confident, we can always go back and think of some discretized version of this path integral. So what I here still wrote is the measure for the path in classical phase space, that's the one we derived. So this is just, so taking the limit of n to infinity, and what we integrate over here is on the phase space slices at every moment in time. Yeah, so we have here the n time slides. And here we have so n free momenta that we integrate over n minus 1 free positions, and this is just due to the fact that that the final and initial coordinates are fixed. So there is one step that one can do, or maybe said probably will make an exercise out of it. So if you pass from the Hamiltonian formulation to the Lagrangian formulation, it's just a simple Gaussian integral to arrive at the action. However, if you really want to figure out the right form of the measure, then you should look at the discrete version. Okay, so to get all the prefactors right, and if you do so, then you will find that the integral measure for the path integral in coordinate space is again given by limit n to infinity. We integrate over all momenta, all positions qn from n equals 1 to n minus 1, again because the zeros in the nth step is fixed by the boundary condition. And then we have this weight here, which just results from the Gaussian integrals over the momenta. Okay, so there's some vector mass times the large n, and then over it, the time 2ph bar to the n half. So this is just something that I just write down here, and now in the first examples we look at all these factors carefully. Now once you start really working with it, normally you're not so much interested in these normalization factors, but in the beginning if you start, it's good doing it right. Now there's this thing that if you want to work out everything fine, at some point you have to go back to the discretized version of the path. So the first thing that we're going to discuss in the example is a free particle, and so the propagator for the free particle, in there then you should go back to the discretized version. Now, once you really start working with the path integral, you normally never do this. So this is just, I think it's good once to be very, I mean, I don't know the word, like, very sharp to sell up and go back to the discretized and count like all the factors that you get, but it's like, never, you probably won't do this too often if you apply the path integral, but it's still good to have done. Okay, that was the original on the path integral. Now what I already said here, so what we typically deal with path integral is always this kind of Gaussian integrals. Okay, so this quickly, the last lesson already recalled. So this is Gaussian integral for vectors in the R to the n. So we have here again some measure. Here's a 2 pi just defined for rotation convenience. But we have before, you have the form of an integral, high dimensional integral of one vector v, which here has some quadratic form given by some symmetric matrix. And here we have the scalar product. And then we couple this vector to some external source. That's how it's normally called. So this is a function of j, and why this is called source becomes then probably more obvious once you come to quantitative theory. So the central integral that we need to know is this kind of Gaussian integral. So we have a quadratic form and some linear coupling. And this integral just gives the determinant of a to some power, and then you end up again with the Gaussian integral, where now we have the source coupled to the inverse of this matrix. Okay? And so I mean, you can just prove this formula by using the one-dimensional Gaussian integrals, using that this is symmetric matrix in combined one. Now, however, you can see is like here, if you look at these integrals, well, they are not exactly of this form. No? So here I wrote down something nice that you know how to do, like we learn the Gaussian integral with real numbers. Okay, so what often happens is that there is an I here in front of it. But this you shouldn't be too worried about, because you know that if you look at the simplest Gaussian integral, like where this is the number a and here some x squared, this gives you the square root of the inverse of this number. Okay, so you can see that this number actually, so the square root, so it's always good at some point to think about not real numbers, but about, okay, explain what I mean. So this would be like the typical Gaussian integral. So this is related to, so there's some factors 2 pi, which I don't care about, 1 over square root a. Okay? So it's good to think of this a not really as a real number, but you can think of it as a complex number. Okay? So you see there's a square root. So the square root is always defined by the log, like for me at least. This is e to the minus 1/2 and then a. Okay? So this is like an analytic function, but has a cut somewhere in the complex plane. So typically at the negative axis. But if you go away from this axis, this is just, I mean, defined on the complex plane. Okay? So you don't have to worry. So you don't have to worry too much about the factors I here appearing, because if you think of it in this way, you can always make sense to it. Okay, that it's defined on the complex plane. Although then it's not a really like e to the I p squared. It's not really an exponentially decaying integral, but what you can always add, you can add some convergence factor, like a very small real part. And then do the integral, so it's just oscillating. But this is just like thinking about how this was a function of a, and you just have to think like where this function is defined in the complex plane. So you don't have to worry too much about here appearing imaginary parts. You can always make some sense of it. If you don't, just ask. Okay. So that was just one thing I should have said last time, because this kind of integral we do when going from the. Okay, so questions or. So what we want to do today is just to make two simple, well, one simple application, which is a free particle for this propagate. So we said that the free particle we can immediately calculate, because we don't have the problem of having an operator consisting of 2 parts which do not commute. We just have the p squared term, so it's easy to go to a p representation and calculate. We just want once as an exercise, which is like something that you wouldn't ever do if you don't want to, like, it's a pedagogical thing. So let's start from the Lagrangian version in this case, and then see how we can derive the result, which you can get immediately by more straightforward word, just to get like a feeling how things work. That's like one example which is technical and doesn't make really a lot of sense, because there we also have to go back to this discretized version, but it's good to once have done this, because there one can then think about the prefactors and everything. It's just good to get like used to these Gaussian integrals. And the second thing is actually the opposite. So this is the first thing is the free particle, which is kind of stupid technical example, but it's good to learn the technical skills. And the other example is the semi-classical limit. So what we see here is that the path integral tells us that the transition amplitude is always given by the sum of a path, where each path is weighted by the classical action divided by h bar. So we see that the action always appears, so there's naturally appears the classical action of a path divided by the quantum scale h bar. So if we are interested in like propagations of particles which are heavy in some sense, which I'll explain, or propagation for some longer ways, the typical action here that appears will be larger than h bar. And somehow we should see that in the limit h bar to 0, the classical word there is. You know, the classical word means that actually, instead of considering here sum of all paths, we should see that the classical path, which extremize the action, should become the relevant path in this integral. And this is then the second thing that we'll discuss as the semi-classical limit. but before, just very something that I don't really know if it's necessary, but I wanted to do it. It's just because we are here now dealing a lot with functions, and then we're dealing with integrals over functions and derivative of functions. So we are dealing with like functional analysis, and I just want to make a very short dictionary of like operations that we usually will have to need. We'll have to know how to deal with. For example, this action here, this is what? This action here, S, is an action here of the phase space trajectory or path x of t. So what do you have? Here you have a path. So you pick one path. It's one path that contributes here. And you insert this path into some function, which is a classical action, and you receive a number. So you have this kind of functionals, which you already know from classical mechanics, which map, instead of like high-dimensional vectors, map functions onto the real numbers. And you have to know how to integrate them and how to differentiate them. And I just make a very superficial dictionary here by always doing what I think, like if you're not that interested in mathematical details, you can always, to understand what is going on, go back to discretized version. Or you can always understand the path as being like the limit of some discretized version. So we can then understand what, or recall what functional analysis like that we need. The very, basic things can be understood as a limit of n to infinity. So let me just then recall like what we're dealing with in normal analysis. So we have functions f and g, which are in R of the n, also not functions, vectors. And then we have some scalar product. Actually, I could have generalized it already to Cn, but it's just possibly apparent. So which is a mapping of the vector space of the product of the vector space with itself to the reals, scalar product, and this is has all the stuff, so it's bilinear and symmetric and so on and so on. So what we do? To the real. Oh yes, thanks. What we normally do is we fix some orthonormal basis, so some ON basis, which commonly we call vector EI. So we have a set of n such vectors which are orthonormal in the sense that the scalar product just gives the tonic delta ij. And then if we have fixed the basis, then we can represent every vector as just a linear combination of these basis vectors, fi, ei, and the coefficient fi is just given by the scalar product of f with the I. Okay. And then we have functions, and we should and let's just say the function is some mapping of the R to the N to the R, the reals, where F is mapped to F, and we want to know like what derivatives are. Okay, just erase this here. This is really very, very short and brief and superficial. Just a reminder to not lose anyone who doesn't recall what functional derivatives are. So just, not would be stupid if one gets confused by these kind of things. So then we can define the partial derivative of the function. So just to make some easy notation, so you can call it del to the del fi, or just abbreviate in this form. You can understand this as the limit epsilon going to 0, and you take the function plus f1 pi and divide by epsilon. So this would be the definition of the partial derivative. And typically what we want to do, like in physics, you often want to do some Taylor expansion of such a function around some reference point. Say we have vectors where f, so we want to evaluate the function at a point f in vector space, and we make a small perturbation g. So the Taylor expansion. Order bj 1 to n I gi plus higher orders. Okay, so just like that's the thing that we normally do. So now I just want to, so after here I recall what would be the functional integrals, we just have to know in the end how to do like Taylor expansion of functionals. So we just have to translate now this to the objects that we are interested in, which are the continuous versions. So this is like taking the limit n to infinity of all these operations. So then f and g, from being vectors in the R of n, become some functions. You can call like a space of functions here just f for their functions. Okay, I don't know. Before we had some n component vector, once we have chosen basis, so this then becomes just a set of f of x where x is in some interval. Okay? So, and we have on this set of functions, we also have typically scalar product, which maps two elements to the reals. Again, I mean, typically afterwards we have some Hermitian product. Let's make it simple. Let's use this real scalar product. And okay, here I already have, in a way, written down expressions once we have fixed the ON basis. So let me just say what the ON basis is. So we can define here also an ON basis in the following way. So here we have just, I mean, vectors which have, I mean, the entries in one of, so they are, you can think of them as vectors just with one entry at one point and then zeros otherwise, and then they're normalized. So if we want to generalize this to the functional, to the functions, then we can do this by defining, instead of these unit vectors, we can define delta functions. No? So the basis would here given by a set of delta functions which are then orthogonal in the sense, so they are now normalized by some here really delta function, and this is like the element where the delta function x evaluated at x prime just gives you normal delta function. Okay, so this is, you can think of this in this way. So then you can define every function as here as a linear combination of your basis vectors. You can now define the function in this way, delta x, where now f of x is the scalar product f of delta x, and the scalar product, which was or I never wrote down the scalar product here, no? The scalar product, once you have chosen the basis, is just, the sum over fi and gi. Okay? Just to make it follow. So here, the scalar product will then be just generalizing this. The sum becomes something continuous, the integral of x, and then you integrate the components, which are here then f of x and g of x. Okay? So the scalar product, I should somehow. Okay, sorry, I'm really bad in this. It's not. I wanted to make it very nice that you can always identify. So this would correspond just to this one. Okay. So then, what we are interested in is in functions which are now called functionals. They map. So not maybe just word. So this is different wording. So we are functional. That is mappings from the space of functions to the reals, or can so later make it complex. And typically in literature, this is now denoted by some square brackets. Okay, so this would be a functional which maps functions to the real. Okay, and it can be always viewed as some continuous limit of mapping a very high dimensional vector, which would be the discretized functions to the real. Okay, and now we can just this is actually what I wanted to go to, so we will need to know how to do the functional derivatives, and this we can now just do in generalizing the high-dimensional vector case into infinity. So we can define the functional derivative with respect here with respect to some coordinate f of I. So we can now define with respect to some function valued at x. So this would be just again notation. This becomes this kind of symbol. Function derivative. Function in some specific direction. So this was first in some direction given by some unit vector. Now we do the generalization with the delta and takes the limit epsilon going to 0. Okay, so it's just using all the analogies. So instead of an R to the n vector with n entries, we are dealing with continuous variables, so we have infinitely many entries, which are here with some position, some interval, and the basis, which was the point basis of unit vectors, becomes the delta functions, which now serve here as a perturbation as into some direction, which defines this x defines the direction. And then in the end, everything that we, I guess, want to do in the end is Taylor expansions of functionals. And actually this, I guess all of you have already done in classical mechanics, because when you externalize actions, this is like how we do it. So we can now again think that G is some small perturbation around F, and we want to make a Taylor expansion around F with small g, so we can again just generalize the discrete case, no? drive in different directions. And so on. Okay? So this is just a brief reminder how to understand like things that will appear now. I mean, probably, I never heard functional analysis, but maybe some of you heard, and so then you probably say, oh, this is all, but very, very basic, okay? So if you have like, don't really understand the object, just think, oh, how was it in R to the n? Well, let's make the translation that in R to the n we have some scalar product, which allows me to define some ON basis. So here in functional space, I typically also have a scalar product that's given by such an integral, and this also allows me to define some ON basis, some way which now has to do with delta functions, and this then allows me to express, think of every vector, that's here, every vector is a linear combination of this basis vector, so we can think of every function as being a linear combination of these deltas, and then we can just think like, okay, what is then if the function is derivative in some certain direction? Well, when we look how the function changes, functional changes if we, so this should be all square brackets, if we make a perturbation in this direction, and this then also leads to the notion of Taylor expansion already. Okay. Questions or no? Okay, so this was just a reminder now, why do we want to deal with it? Well, so this will become in the semi-classical, the discussion of the semi-classical limit, because we already said, okay, so the path integral is given as an integral of all possible paths weighted by some action. And we know that actions, the classical actions should play a prominent role in the limit where the typical action scales associated with paths and propagated are much larger in h bar. So we want to there exactly make this kind of analysis. So we want to see like what is the contribution from paths which let's say are classical and then deviations from classical paths. So there this will be needed. But first we'll discuss one example of the path integral for the free particle. Okay, so just the outline of the rest of the lecture. So this was all kind of the review and some reminders. This is path integral at work. And we discussed two examples, free particle, and then discuss the semi-classical limit. So let's first start with the free particle, meaning we're considering the problem, again, just for simplicity, one-dimensional problem, but the generalization to d-dimensional straightforward, just Hamiltonian given by kinetic energy, okay? And as already said several times, one can readily calculate then this transition amplitude by using that, you know, the eigenfunctions of this operator, which are the momentum states, by inserting here a resolution of the unit operator in Hilbert space in terms of the p basis. No? Then we end up with some integral, which is due to the representation of the unit operator. Then we have here the operator just becomes the p squared, I mean the eigenvalues, and then we have here some overlap, which is plane waves. So we have p with qf and p with qi. So this gives some e to the I, p times qf minus qi. And then there was this integral over p squared. So this is a simple Gaussian integral, which then will give us a qf minus qi squared, something like this. Okay, and then if one works everything out with the right prefactors, one derives at the following. So this should be one thing that I think would be good to once do this at home. I mean, it's just a Gaussian integral, and again there now you might want to think about having a Gaussian integral which is not exponentially decaying but just an oscillating function, so you have the I. But with what I've said before, I hope you're not getting scared of this kind of integrals which somehow look first not really convergent. So this is the result that one should get from such a simple calculation, okay? Just one Gaussian integral. So this is the factor which comes from, I mean, the determinant in the one-dimensional case is 1 over the real number that's in the exponent, so the time used in h bar and all this. And this is just from the Gaussian integral, and this is qf minus qi squared. Okay? So let me just make a few comments on this because this is actually quite interesting. So, okay, questions, or I mean, just I think it's just a good exercise to do it once. But the idea how to do this. So let me write this in the following form. So what we find is we have some function which is t-dependent, and then we have e to the I divided by h bar with some function which I now call the action of a classical path. Well, why do I call it the action of the classical path? Because what is written here, then if I take away I over h bar, it's m times qf minus qi squared divided by 2t. So this is a free particle where I just go on a straight line. Okay, so this, if you think about it, this is just like giving the velocity, if I divide by t, yeah, that I go with constant velocity. Now for the action, I still have to integrate the Lagrangian over time, so I get another factor of t. So this here is really the classical action of the classical path connecting points qf and qi in time t. Okay? Just write this down. Classical action of the here unique classical path connecting qi and qf for final initial coordinates time t. Okay? So what we find in case of the free particle is a specific structure. Actually, this function here is also related, and I come back to this, to the classical action. So if you just look at this, is the square root of some object m over t, which is in a way related to the mixed derivative of this classical action with respect to qf and qi. Okay? It's just one comment that we will come back to this. So we find a very specific form of this propagator, and actually in the next part, when we come to the semi-classical limit, what I actually want to discuss is that this form is actually very typical to appear. So you find the exponential classical action of the classical path in some what is called fluctuation determinant, why it also should become obvious once we discuss, which is related to derivatives of the classical action with respect to the initial and final coordinates. So this actually structure appears always in quadratic problems. We will discuss this. So this is the simplest quadratic problem where we just have a free particle. Another quadratic problem where we only have operators in quadratic order will be the harmonic oscillator, p squared plus q squared. So this will be discussed next time. And it appears in quadratic problems, and it appears always as a first approximation in the semi-classical limit. Okay, semi-classical. Okay, so what we now want to do is something very stupid, because I need to derive this in a very straightforward way, or you can derive this in a straightforward way. We just want to do as a consistency check to see how to derive this transition amplitude now using the path integral. And the stupid thing there is that, well, if you want to use the path integral and we really want to get out all the prefactors right, then we should go to the discretized version. So as I said in the beginning, this is something that later on we'll never do again, but it's good to once have this done. And afterwards, in many calculations, you do not so much care about like this prefactor here, because you can always relate it, like if you once calculated it for the free particle, now if you want to do the calculation for the harmonic oscillator or whatever, you can always get the right normalization by using some reference path integral. Also, you can always say, well, there should be some time-dependent function in the front, which now I can get like for the harmonic oscillator, but by just setting like, if you have omega times q squared, setting omega to 0, I know I should get the free particle, so I don't care so much. I know what should be there. Okay? So it's good to have done this calculation of the free particle once explicitly, although it's kind of doesn't, I think it's kind of only a technical exercise, but one should have done it once, especially if one then wants to use it as a reference. So this will take probably a couple of minutes, so it's not really fun doing it, but one should have done it once. So the derivation of this expression here using the path integral. Derivation using the path integral, and what I will do here, use the path integral in the use the path integral in the Lagrangian formulation. So what I write down now is the transition amplitude for this object here using the discretized version of the Lagrangian path integral, okay, which I have written down in general form at the beginning of the lecture. So we start out from discretized version. This was the measure of the path integral in coordinate space Yeah, actually I don't write it down from the discretized version, but from the, okay, I took the phrase already, because I write here the limit at infinity, so it's the very precise version. So this was a measure that we have never derived, which I just mentioned, and which you get if you do the Gaussian integrals over these when changing from the Hamiltonian to the Lagrangian version. And then and for integral with boundary conditions Q0 is Q initial and Qn the final. And then we have the exponential of the action in Lagrangian formulation, which is here written in the discretized version. So instead of having a time integral, we have here a sum over the time steps, and what we sum is the kinetic energy. So it should be the derivative of the q's. Okay, so this would be q dot. So there should be a 1 over t squared. There's a 1 over t because we have one t over n, which is from the writing the sum as writing the integral over time as a discrete group. So this is just the discretized version in time of the Lagrangian. Yes. Okay. So this is just, I mean, so we know that it's in the way dt q dot squared m half. So we have m half h over I over h, and then this n over t is just 1 over the small time step delta t. Okay. So if we take q dot, this will give us qn plus 1 minus qn over delta t squared. Then we have the integral becomes like a sum with the delta t. So what this gives us 1 over delta t squared, this gives us delta t. So we should have a 1 over delta t, which is the n over t. Okay? You can go through it. So now what we just want to do is we want to integrate out all these intermediate coordinates. Okay? So Q0 is Q initial, Qn is Q final, but Q1 to Qn minus 1 and so on, you can just integrate out. Okay, so this is just doing stupid Gaussian integrals. So let me just write this out here explicitly. So this is Qn minus 1 squared. So this here is Q final plus and so on, and then we have Q2 minus Q1 squared plus Q1 minus Q0, which is Q initial. No? So in the first step, well, we can integrate just over Q1. So if we multiply all this out, we get a Q1 squared from here, we get a Q1 squared from here, and then we have some linear term where Q1 couples to Q initial and Q dot. Okay? So it's just a simple Gaussian integral. So this we can do once. So let me just try to see. So let us only collect those terms which depend on Q1, and let us use the following identity, which is IQ Q1 into I m and h bar t. So this is just now connecting those terms which depend on q1. Q initial squared. Okay? So I just collected those terms appearing here, and I wrote down here one of the factors. So we have many of these factors, and for convenience, I just write down the expression of this. Okay? So I just give now what this will give. It's a simple Gaussian integral. If you apply the formulas, you should arrive at the following expression. So again, it's good to do this maybe once. Okay, so just briefly to motivate you, what you get here, you get a q2 squared, you get a q1 squared, a q1 squared, a qi squared. So the q2 squared and the q initial squared, they don't depend on q1, you just put them out. But then we get the coupling of q2 to q1, q times q1, q1 times q initial. And they are integrated over the integral q1, which is squared, which will give us a q2 plus q initial squared. Now, combining those with the q2 squared and q1 squared, which already appeared here, one can see that one can divide this in a nice form, which is q2 minus q0 squared. Okay? So this is very nice because we see that, like taking those two contributions, we arrive at something which is just looks very identical, like the one which would have had if q1 wasn't here. Okay? So this is then again, if we add this now to this integral here, we will just have the same kind of sum here, only that the n equals 1 contribution was eliminated. Okay? This is just the result from the Gaussian integral, integrating over q1. But we see something interesting, and this is now, if you compare this expression with this one here, we see, well, there appears the time 2 times instead of the time t. Okay? So all these contributions here, qn plus 1 minus qn, appear with a t, and here with a 2t. Okay? Now, in the same way, the normalization factor here was 2ph bar times it, while here we have again a factor of 2. Okay? So this is one difference that appears, and now it's just, I mean, this really isn't too much fun, but try to do it. Now it's just keeping track of these factors too. So we see that after integrating here in this product of q integral over qn minus 1, qn minus 2, q3, q2, q1, blah, 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 we integrate over q1. You still have to do the integral over n minus 1, n minus 2, blah, blah, q3, q2. But we see that the q2 integral now has changed from, if we just would have taken this one, where n equals to 1 wasn't present, so we would have here q3 minus q2 squared, q2 minus q0 squared, okay? But the prefactor here changed by a factor of 2. Okay? But instead of this, all the integral is just identical. So what do? We do exactly the same way, the same as we did here. So we collect all the terms which depend on q2. So this will be here q3 minus q2 squared, and then we have q2 minus q0 squared, and we just integrate over q2. Okay, and I just give the intermediate step here. So what we do is give this here. So what we did so far is we wrote down the propagator in the discretized version. We know we have to complete n minus 1 integrals. We did the first. And we said that the structure is very much as it has been before, only with 2 differences of factors 2. So let's make the next integral. So we integrate now over q2. Or questions? So it might be a little confusing, but if you sit down at home and you kind of recall what I said, I hope it makes sense to you. So it's just keeping a book of all the factors. So what we want to do now is we want to integrate over Q2. We still have all this normalization factor here, which we should somehow work into our calculation, because in the end we know that this should just give like one factor with a square root, so the end should have disappeared. So let's do the next integral over Q2 and take another factor of this one. Okay, we already took two factors here, so let's take another factor of here, multiply this with this, and then do the integral over Q2. Okay? So multiply this expression here with one of the factors from the normalization, which comes with IT, pH bar with 1/2, and then with the weight that we still have to add in the sum, which depends on Q2. So this is the one contribution which is Q3 minus Q2. Okay? So this is just taking this big product, taking the one term that depends here on Q2, this depends on Q2, takes this one normalization factor, and now do the integral over Q2, okay? So again, what you write is, and integrate over Q2. So the integral itself is again a simple Gaussian integral, because it is Q0 here squared, we have some Q0 squared, or Q initial, I should write here, and then there's a coupling, Q2 times Q1. Here again we have some Q3 squared, it doesn't depend on Q2. We get a Q2 squared and a coupling Q3 minus Q2. So this integral over Q2 will give us something like Q3 plus Q initial squared, and we have to combine Q3 minus plus Q1 squared with Q3 squared and the Q initial squared that we pulled out here in the beginning. And we just see, well, it's basically the same thing as we did here. The only difference is that here we have a factor 2t and not a factor t. So if you go carefully through this calculation, you will find that what you get, that the result is similar, or it's identical actually, to what we got here, where only you have to substitute the following. To substitute. Well, first of all, of course, it shouldn't depend anymore on Q2, because we integrated over Q2, but in the same way as integrating here over Q1, that is something that depends on Q2 minus Q initial. Now integrating here over Q2, well, it should depend on Q3 minus Q initial, no? So you have to substitute. Well, this is just because the structure is identical, but it's good to check. Okay, Q0 is Q initial. I somehow mix it up, but let me just stay with Q0, okay? And then what we saw here, well, there was one difference, is that we had here a 2t appearing and a 2t appearing here, okay? So let me just call this 2t, and if we do here the integral, these factors 2t at two places, which appeared, now become a little bit more evolved, because we have, once we have a factor like 2t here, but from this you just have a t, okay? So if you combine these in the right way, you should find that this becomes now a 3t at the two places, okay? Let me just write at two places, and what I mean is, at one place is come out with the Gaussian weight, which now has a factor 3, and the normalization factor also has a factor 3. Okay? So this is what you find. Actually, I can write down Yeah, I'm really very, very detailed here, but maybe it's helpful, I don't know. So what I mean is that you get this 3t. So what do you want to do next? Well, just proceed in the same step. So let's multiply again with one factor. From this, multiply with whatever still depends on Q3 and do the Gaussian integral over Q3. So anyone has a guess what comes out if you do this? So if you integrate over Q3, well, you get Q4 minus Q0 squared. Well, you could imagine that this becomes a 4, and this also becomes a 4. Okay, so if you do this iteratively now n minus 1 times, then actually if you see now how it works, like how the factors combine, you can imagine that doing this n minus 1 times, well, first of all, you arrive at an expression that will depend on Q naught or Q0 minus Qn squared, which is Q final minus Q initial squared. So you have e to the minus Q0 squared. Then you have n 2h bar, and what you find is that you get here the factor n, okay? N times t. And then in the normalization factor, there should remain an n over n. And then again, because you keep increasing this number in front of the t, you get an n times I t ph bar. Okay? So this is just the factors n that appear generalizing this step into one time. Okay? So you see the ends just drop out here, and you arrive at what should be there. But it's just going once, sit once down and do 2 integrals. Maybe if you're smart and you just have one and have to do just integral over Q1 and you already see how it works. I have to do 2 over Q1 and Q2. But then you can see like how it works, and I mean you arrive there, and what you learned is just, well, you did some kind of stupid calculation, but you learn how to work with these integrals, and it's, I think, useful to do this kind of things at some point. Okay, questions or? Okay, so this was the kind of calculation part, and then we come to, I think, conceptually more interesting to the semi-classical limit. Just make 5 minutes ready. Okay?